Uh, Hello to everyone. My name is My name is Timur Aslyamov. I'm a postdoc in the group of Massimiliano Esposito and from University of Luxembourg. And today I would like to present our recent results about non-equilibrium static responses for Markov jump process. We studied directed graph with Markov jump processes over discrete states where transitions is defined by rate matrix with arbitrary parameterization in terms of vector p. So we focus on non-equilibrium steady state, which implies that current and traffic defined here, they depend on parameters p explicitly because of expressions for rates, which are known, and implicitly because of solution for for steady state probability. And to account for this behavior, we introduce static response as an element of matrices, which is just total derivatives of observables, of the elements of the set of observables in respect of all parameters, which could be arbitrary here. And the first part of our results is dedicated to certain assumption about rate matrix, and it is about Arrhenius-like parameterization, which is similar to distribution at the energy landscape with the barrier heights B, some state-dependent potential energy, and antisymmetric contribution from non-conservative force. And from the literature, only exact results for response to potential energy was known from the paper of Owen, Gingrich, and Horowitz. And in our paper, we developed a linear algebra-based approach which allows us to find compact expressions for all three responses. So these responses of probability to all three parameters of rates. And as one can see from these exact expressions, the responses for barrier and forces, they show explicit dependence on current and traffic for the same edge as the edge of perturbation. Also, from linear algebra, we showed that this coefficient D can be calculated as the product of all non-zero eigenvalues, and we assume irreducible rate matrix, which says that those eigenvalues are negative. And for parameter kappa, we showed that this kappa kappa could be complicated, especially for large networks, but this kappa doesn't depend on the edge parameter. So in this case, doesn't depend on BE and FE. So these exact expressions gives this very simple result. For example, if we consider the response to barrier over probabilities P for this certain example as a function of force, of edge force, we can find that all responses are zero if we equilibrated only one edge, the edge of perturbations. But other system is still non-equilibrium. So other J and affinities are non-zero. Also using these results and chain rule, we can calculate the responses for current and for traffic and find similar expressions. But more interesting to consider bounds for them, because those bounds have a remarkably simple expression. And if we write them in terms of sensitivity, so it is like log of this derivative, we find that they're universal and they don't depend on topology of your network. And for this first part of results, beside Arrhenius-like form, we also considered only local responses, which means we perturb and measure the same edge. Here it is denoted by the same index E for response and derivative. But if we lose this assumption and we consider responses to all, observable responses to all parameters, we find this. We find that these responses are not independent, and it could be illustrated by this simple example where we don't make any assumptions about certain form of rate matrix, but we assume that it is a homogeneous. So means homogeneous function of some parameter or vector h. Then with restrictions on non-equilibrium steady state and unique solution for irreducible matrices, we find that probability is a function of homogeneity zero order. So it is this power k. But current has the same homogeneity order, so the same homogeneity property as a rate matrices, just because by the definition and property of pi. And applying Euler theorem, we can find equivalent description for this homogeneity property in terms of these linear relations, which we called summation response relations, which are linear combination of the responses to all parameters. Important that they explicitly depend on the choice of parameter because of this coefficient h, which is parameters, but they don't depend on topology. So they have the same form for all possible networks. Going beyond this example, and if we consider an arbitrary parameterization, we can define this information in terms of Jacobian. And then in the case when the number of parameters equal or larger the number of edges, we can find general expressions for summation response relations, which is very similar to example, but now we have a more complicated dependence of parameter in terms of this pseudo-inverse acting on the current. But if we proceed with this special case of parameterization when the number of parameters equal the number of edges, and moreover, we have access to independent perturbation of every edge, our Jacobian matrix will be diagonal, and pseudo-inverse became just invertible matrix, and all these calculations now is straightforward. So for this case, we found generalization of our previous results because all local responses when parameter of edge perturbation is the same as edge of observable, with this simple scale, those responses are bounded. So it means our previous result can be extended beyond Arrhenius-like form. And moreover, we found a new linear restriction, which we call cycles response relation, which says that those local responses, they sum up to the number of Schnachenberg cycles, which is topological cycles, and unlike previous summation response relations, this kind of restrictions depend on the topology. And this information is crucial if we consider, for example, unicyclic networks. Well, in this case, with edge perturbations, we proved that not only local responses, but all responses are bounded between 0 and 1. And here we can calculate all configurations of edges. And also, linear restrictions can be written in the following form, which says that if we fixed edge, and calculated sum of all responses, they sum up to 1. And again, comparing with this bound, if we saturate one of our responses, other responses must be 0. Yeah.
Timur,
and
you start to be finishing up?
Okay, yeah. In the last slide. Yeah, and from these iterations, we can see that normally response is distributed over all parameters, but sometimes one dominates. So, but it is always between 0 and 1 for some. And briefly, we can extend this result to multi-cycle networks. For example, for this system of 3 cycles, we can prove that all local responses bounded. And by cycle response relation, their sum always should be equal to 3 because the number of cycles is 3. Okay, local responses are bounded, but since the responses in general, they are not independent, some of non-local responses can be rewritten in terms of linear combination of local ones. And then they also will be bounded as a linear combination of bounded responses. And we can show that here 20 responses among 36 are bounded. So it is more than half. And they bounded between -1 and 1. Yeah. And to conclude, there is the papers of this about these results. So the first one about Arrhenius-like perturbation, and recently we generalized our results to arbitrary parameterizations and found linear restrictions that we consider non-local responses. Thank you.